moving into section 17.2, measuring and expressing enthalpy changes. So we'll look at what enthalpy is. We're at the bottom of page 6. My battery's dead. Awesome. All right, so how can you measure the change of enthalpy in a reaction? Calorimetry is the measurement of the heat flow into or out of a system for chemical and physical processes. In a calorimetry experiment involving an endothermic process, the heat absorbed by the system would be equal to the heat that is released by the surroundings. Remember, from a universal perspective, there is no gain or loss of heat. It is given off by the system and absorbed by the surroundings, or vice versa. So the net change of energy in the universe remains constant. In an exothermic process, the heat released by the system would be equal to the heat that's absorbed by its surroundings. And so there's a device that's used to measure these types of changes, and it's called a calorimeter. So it is used to measure the absorption or the release of heat in a chemical or physical process. And I have a picture of what these look like on the next page. So here's a calorimeter. It can be as low tech as 2 styrofoam cups stacked inside of each other. So what you do is you have, typically occurs in an aqueous solution, so you have a fair amount of water. There is a stirrer through a hole in the lid. The lid is loose fitting here. The foam cups are nested, so they're stacked inside of each other for insulation. You have a thermometer going into the solution, so it can measure the temperature changes that are occurring. And within the water is where the reaction is going to take place. So you take a measurement of the solution before you add in your reactants, and then you stir it and let the reaction occur, and look at if the temperature increased or decreased. It would, in this situation, it would be within the water. So the heat would be measured in the water. Either there's a temperature decrease or there's a temperature increase because of the reaction. Insulate means that it slows down the transfer of heat either into that cup or out of the cup. So it insulates it from that change. All right, so enthalpy is given a capital H as an abbreviation when we're looking at it in formulas. So the enthalpy of a system accounts for the heat flow of this system at a constant pressure. And the heat that is absorbed or released by a reaction at this constant pressure would be the same as the change in enthalpy, which is shown as delta H, or triangle H. So the value of that change in enthalpy of a reaction can be determined by measuring the heat flow of the reaction at a constant pressure. So we can interchange the words heat and enthalpy change. We saw that the little lowercase q was used to refer to heat in our formulas that we learned in our previous notes. And so the heat, or Q, is equal to the enthalpy change, or that delta H. To measure the enthalpy change for a reaction in an aqueous solution within a constant pressure calorimeter, you have to dissolve the reactant chemicals, which would be the actual system. So the chemicals that are having that reaction would be referred to as the system. And it is occurring in its surroundings, which is a known volume of water. You would have to measure the initial temperature of each solution, so the reactants and also the water that you're going to be having this reaction occur in, and you're going to mix the solutions in the calorimeter. After the reaction is complete, measure the final temperature of these mixed solutions together. So that way you can see if the temperature increased or the temperature decreased, and you would be able to tell if it's an endothermic or exothermic reaction. All right, you can calculate the heat absorbed or released by the surroundings. So that the heat of the surroundings is shown with a Q and then the abbreviation of SURR for surroundings. So we actually use the formula for specific heat, the initial and final temperatures, and you also have to know the heat capacity of water. You need to know how much energy it's going to take in order to raise the temperature of water by 1 degree Celsius. So we have this formula. The heat of the surroundings is equal to the mass times the specific heat of water times the change in temperature. And the way that we find change in temperature is we take our final temperature minus our initial temperature, and those measurements are always in degrees Celsius. So the heat absorbed by the surroundings is equal to, but it has the opposite sign of the heat that's released by the system. So we use positive and negative signs to show basically the direction that heat is traveling. So the Q of the system, the heat of the system, is equal to the enthalpy change. The heat of the system is also equal to the negative of the heat of the surroundings. There's another type of calorimeter. Here's a picture of it here. So the previous calorimeter was being done under constant pressure. So the entire experiment occurred with the pressure being held constant. But calorimetry experiments can also be performed at a constant volume using a device called a bomb calorimeter. So in a bomb calorimeter, a sample of a compound is burned in a constant volume chamber in the presence of oxygen at a high pressure. There is a sample that's being burned inside this little copper dish here. There's some kind of a firing element. This is an oxygen-rich environment within that compartment. So this would work if you were trying to do an experiment that you couldn't have submerged under water or in an aqueous solution. So there is oxygen under high pressure. You have this sealed canister, and then around it is water. This metal canister that it's in would be a good conductor of heat. So whatever temperature changes are occurring within this little compartment would be easily transmitted to the water outside, and there's a thermometer measuring the heat of that volume of water. So by measuring the temperature increase of the water, it's possible to calculate the quantity of heat that's released during a combustion reaction. And remember, combustion means that something is reacting with oxygen. All right, page 8. All right, so we're going to do an actual calculation looking at some of these situations here. It says the initial temperature of the water in a constant pressure calorimeter. So that would be like the first example of a calorimeter with the kind with the 2 styrofoam cups. The initial temperature is 24 degrees Celsius. A reaction takes place in the calorimeter and the temperature rises to 87 degrees Celsius. So we can find our change in temperature by going our final temperature minus our initial temperature. So 87 minus 24. The calorimeter contains 367 grams of water. So that is our mass. And we know that the specific heat of water is something that we could look up on a table. And so it gives us the specific heat of water is 4.18 joules per gram degrees Celsius. Again, specific heat has a very long unit, a very long label. Calculate the enthalpy change during this reaction. So we've labeled all of our variables. We have mass, we have specific heat, we have change in temperature, and so we're looking for the enthalpy change, which is at delta H. The only thing we need to solve for is what is our actual temperature change. We have the final temperature minus the initial temperature, so 87 minus 24 gives us a temperature change of 63 degrees. And we keep that in Celsius because our specific heat is looking at the change that it takes to move 1 degree Celsius. All right, so now we're ready to plug this in. So the formula that we're going to use is right there. We have mass times specific heat times change in temperature. There is a negative sign in front of it because the enthalpy change is equal to the negative of all these variables. So don't forget the negative sign there. Our mass is 367 grams. Our specific heat is 4.18. Our change in temperature is 63. So we're going to end up multiplying these three values together. So 367 times 4.18 times 63. We have a lot of units, so we'll just list them all off to the side here, and then we'll figure out what gets reduced. So we have like negative 96,645.78. Our units on the top, we have grams, joules, degrees Celsius. On the bottom, we have grams and degrees Celsius. So the grams are going to cancel each other out, and the degrees Celsius are going to cancel each other out, and the only unit that's left behind would be joules. And that makes sense because heat is measured in joules, energy is measured in joules as well. As we're looking at significant digits, the least amount of significant digits came from our temperature readings. We only had 2 digits on both of our temperature readings, so that means that our answer is going to be limited to 2 digits as well. So our final answer would be negative 97,000 joules.